The expression that we are calculating is dx1, dx2, dx3 e to the power minus I p1 dot x1 plus p2 dot x2 plus p3 dot x3 times I times g. The diagram is this one. The vertex is at y. These are x1, x2, and x3. So the vertex factor is I times g times the dy integral 1 over I delta x1 minus y 1 over I delta x2 minus y 1 over I delta x3 minus y. Then we write the propagators in the momentum integral of over momental language. Dx1, dx2, dx3, and then there are 3 propagators, so there will be 3 momentum integral. Those and e to the power minus I sum over I pi dot xi times e to the power I q1 dot x1 minus y plus I q2 dot x2 minus y plus I q3 dot x3 minus y, then 1 over I delta tilde q1, 1 over I delta tilde q2, 1 over I delta tilde q3. And then, as usual, as we did in the last calculation, you do the x integrals to get a bunch of delta functions, and those will be given by the following. So x1 has minus p1, x1 has minus p1 and plus q1. So that will be 2 pi to the power d delta p1 minus q1. Then x2 has minus p plus q2, so 2 pi to the power d delta p2 minus q2 and 2 pi to the power d delta p3 minus q3. And you will be left with the exponential involving y, and that will be e to the power I minus I sum over I qi dot y, because this is minus q1 dot y minus q2 dot y minus q3 dot y. Okay, and then you have these propagators, momentum space propagators. So you perform the Q integrals and both the Q integrals and the Y integral. If you do the Y integrals, so Q integrals will can be done, and all the Q's will be set to the corresponding P's. Like P1 will become P1, Q2 will become P2, and Q3 will become P3. Now this y integral here has only this, and that gives you a delta function over sum over I qi, but that is same as sum over I pi because of these delta functions. So one has 2 pi to the power d, that is coming from the y integral delta p1 plus p2 plus p3 times 1 over I delta tilde p1, 1 over I delta tilde p2, 1 over I delta tilde p3. So this diagram, so that means your original calculation will be, so therefore G tilde 3 P1 comma P2 comma P3 times 2 pi to the power d delta P1 plus P2 plus P3. If you calculate, then the first term that appears from the position space Feynman diagrams is this one, and we will be drawing a momentum space diagram here. And as usual, I mean, like we did before, for these are the momentum space propagators. So there will be 3 lines with carrying 3 different momenta, P1, P2, P3, and P1, P2, P3 are the external momenta, and there's a vertex factor, and then there is an overall conservation of the momentum. And also, as I discussed before, you have to have, so there are 3 lines meeting together, and then each one carrying momentum. The momentum can be either along the line or, I mean, momentum can be either incoming or outgoing. Each one has a momentum. So this is say P1, this is P2, and this is P3. But then P is a momentum, and therefore it has a, so it has to be either the momentum is along the, since it's a vector, it's along the either it's incoming or outgoing. So if I take one of them to be incoming, then I should take all of them to be incoming, because in the formula, in the whatever I'm calculating here, all the p's have been taken to be same sign, right? So there is no reason why I would choose one, why you would see one to be incoming and the other to be outgoing. So you have to choose either incoming or outgoing for all of them if you have defined your calculation with this same sign p's. And then there is a vertex. So and these higher order terms, this particular diagram corresponds to this contribution that we just calculated. So this is this diagram. Okay. So in the first calculation, in G tilde 2, we identified the propagator. Then in G tilde 3, we identify the vertex. Now there is another feature in the diagram, which is the loop. So that let's consider the simplest diagram with a loop, and that's the G square correction to the propagator. So contribution to G tilde 2 P1 comma P2 from this diagram. Okay, let's calculate that. And that is integral dx1 dx2 e to the power minus I p1 dot x1 plus p2 dot x2 times ig integral dz1, ig integral dz2. There are two vertices, and then there are propagators, one from x1 to z, the first vertex, then from z1, first vertex is z1, z1 to z2, and there are two of them, so 1 over I delta z1 minus z2, and then 1 over I z2 minus x. Then we now we write the propagators in the momentum integral form, dq1 over 2 pi to the power d for the first propagator. Then the second propagator, I write dq over 2 pi to the power d, and there's another repetition. Third one is dq tilde over 2 pi to the power d, and the last one is dq2 over 2 pi to the power d. So what I've done is that I have taken the momentum, the symbol for the momentum that I've taken for this one is q1, and for this one q2, this one q2, and this for this one q and this one q tilde. They are same, but nonetheless they will have two different momentum integrals. Then you have this e to the power minus I p1 dot x1 plus p2 dot x2, and then the phases in the propagators, and those that is given by e to the power I q1 dot x1 minus z1 plus I q dot z1 minus z2 plus I q tilde dot z1 minus z2 plus I q2 dot z2 minus x, and the corresponding propagators in momentum space q1 1 over I delta tilde q 1 over I delta tilde q tilde 1 over I delta tilde q2. Then we will be doing this x integral. X integrals will produce p1 delta function p1 minus q. Sorry, this should be q1, p1 minus q1, and this is x1, and this is z2 minus x2. This is x2. And so x2 integral will give you p2 plus q2, right? So this is ig whole square integral dz1 dz2 dq1 over 2 pi to the power d dq over 2 pi to the power d dq tilde over 2 pi to the power d dq2 over 2 pi to the power d. Then x1 and x2 integrals will give you delta function p1 minus q1 and P2 plus Q2. So that will be 2 pi to the power d delta P1 minus Q1, then 2 pi to the power d P2 plus Q2. Apart from that, the other phases will involve Z1 and Z2, and those are, let us figure that out. For Z1, I have minus Q1 plus Q tilde plus Q2. So e to the power I minus Q1 plus Q tilde plus Q2 dot Z1. Sorry, there is no Q2 because Q2 multiplies Z2 only. There is no Q2 factor in Z1. So that is a mistake. So this is not there. So this dot Z1. Similarly, for Z2, you have minus Q tilde minus Q tilde plus Q2 minus Q tilde plus Q2. Minus Q tilde plus Q2 dot Z2. So those are all these X and Z integrals. And then we have this bunch of propagators. Q1, Q tilde, and Q2. So 1 over I delta tilde Q1, Q1, 1 over I delta tilde Q, 1 over I delta tilde Q tilde times 1 over I delta tilde Q2. So now we can impose this Q1 and Q2 integral delta functions. So that will be Ig square integral dz1 dz2. Q1 and Q2 integrals are gone. dq over 2 pi to the power d dq tilde over 2 pi to the power d times e to the power I minus Q1 is P1 plus Q tilde dot Z1 e to the power I minus Q tilde plus P2 dot Z2. 1 over I delta tilde Q1 is P1, 1 over I delta tilde Q, 1 over I delta tilde Q tilde, and this P2. Now I can perform Z1 and Z2 integrals, and they will also give the delta functions. Z1 integral will give 2 pi to the power d delta q plus q tilde minus p1, and z2 integral will give 2 pi to the power d delta p2 minus q tilde. I mean, let me write it this way, q plus q tilde minus p2. Then 1 over I, this is the same. Then perform q and q tilde integral. So if we, you see, if we perform q tilde integral, then we have let us first perform 2 pi to the power d are all cancelled. Let us first perform q tilde integral. So q tilde is p1 minus q. So that will be here, delta q tilde is p1 minus q. When you write q tilde equals p1 minus q, then there is something is wrong here. Let me check. So what the mistake that I made here is this is minus q tilde plus q2, but then when I replace q2 by p2, I should have replaced it by minus p2 because it is delta function p2 plus q2. So this should be minus p2. And therefore, I should have plus p2 here, q plus q tilde plus p2. Now, if I do q tilde integration, then q tilde is p minus q. When I write p minus q here, that minus q and plus q cancel, so p1 plus p2. So delta p1 plus p2. Right, and then 1 over I delta tilde p1, 1 over I delta tilde q, 1 over I delta tilde q tilde. Q tilde is p1 minus q minus q, and the last one is 1 over I delta tilde p2. Now, in this, let me at this stage, I can change q to minus q, because q integral is minus infinity to plus infinity. So if you change q to minus q, just change q in the integrand. This remains the same. This integrand in the integrand q goes to minus q. Delta my q is same as delta minus q, so it remains the same, and it becomes plus. This is just a change that I'm doing because of I want to draw the diagram in a particular way. You will see that in a moment. So this is the result, Ig whole square 2 pi to the power d, the delta function for overall momentum conservation, then 1 over I delta tilde p1, and then we have a q integral. I have written an extra factor of 2 pi to the power d in front, so I have to compensate by writing it this way. And 1 over I delta tilde q, this is the q dependent, these are the q dependent propagators, and then finally 1 over I delta tilde P2. Now, the question is, how do we interpret that diagrammatically? Probably you must have guessed by now that the diagram looks exactly same as in the position space, except that the labeling of the diagrams change. In position space, the diagram has some external points, but in momentum space, the diagrams will have external momentum. So, so this delta P1 and delta tilde P1 and delta tilde P2, these are the propagators for the external lines with external momentum. So this is your P1, and the diagram was like this, and this is your P2, both incoming. But then if you interpret what Q is, you see at the vertex you have a propagator which is with carrying momentum Q, which is this one. Then this one is P plus Q. I mean, this is P1, so P1 plus Q. This is the second, this propagator. So this propagator is this one, and this propagator is this one. So what it shows that, first of all, there are two vertices, and I have Ig to the power 2, and these are vertex factors. Then there's that overall momentum conservation delta function, and then for each propagator I have the propagators, but there is a momentum that is running inside the loop, this Q value momentum. When P comes in, this momentum becomes P plus Q, and then P goes away because P1 goes away, because this P1 going away is minus P1, which is same as P2. So P2 coming in means P1 is going away, and then from P1 plus Q, P1 is going away, so you have Q here. So Q is running inside the along the loop. P1 is coming, going along with it, and then leaving. So one striking fact is that there is not only an overall momentum conservation, which is given by this, but because of this particular way the momenta appeared, especially the internal momentum, which is integrated over. That momentum is not an external momentum. It's an Q is an internal momentum, in the sense that it does not have a fixed value. It is running from minus infinity to plus infinity. It's an internal momentum running in the loop. Whenever you have a loop, there is a momentum running inside the loop. The momentum specification labeling of various parts of the loop, the propagators, will have the labeling depending on what kind of external momenta are coming in. But when you after you label everything, all these propagators properly, then you will see there is an extra momentum which is not fixed by the external momentum. So that momentum is running inside the loop and going from minus me to plus me. That's called a loop momentum. It's an internal momentum. Now, the striking fact that I was going to mention is that not only there is an overall momentum, there is an overall momentum conservation here, but after you figured out the leveling right properly, the leveling of all the momentum leveling of all these lines, then you see at each vertex the total incoming momentum is 0. There's a conservation of momentum at each vertex. So P1 is coming in and Q1 is coming in, P1 plus Q going out, which is same as minus P1 plus Q coming in. So P1 plus Q and minus P1 plus Q gives you 0. Similarly here, it is P1 plus Q coming in and P2 coming in and Q going out, which means minus Q coming in, P1 plus Q coming in, minus Q coming in, and P2 coming in, which is minus P1 coming in. So P1 plus PQ coming in and minus P minus Q coming in, which cancel, and therefore total incoming momentum is 0. This is one way of looking at it, that just calculate the total incoming momenta, or you can convince yourself that P1 is coming in, Q is coming in, P1 plus Q is going out, same amount should go out, so that there is a momentum conservation at the vertices. So this is basically the fact, this is basically the result of the Z integral. So originally these vertices were in the position space Z1 and Z2. If you look at the Z integrals, and that gives you the that's where your momentum conservation at the vertex is maintained. These are the basically the phases which are forcing the momentum conservation. Of course, you have independent momenta Q1, Q2, etc., but they are forced to be external momenta by the other delta functions. But other than that, the total momentum coming into the vertex Z1 and vertices Z1 and Z2 are 0. So this is momentum conservation at each vertex. Okay, so I shall now calculate one more to demonstrate how the momentum integrals appear in loops, which is a vacuum diagram. So far all the diagrams that I have calculated have external lines, but let me calculate one without any external line in the next part.